Alright, hey guys, welcome to SurviveIB, and tonight we're going to do some physics homework on momentum and impulse. And before we start, I'm going to do a really quick definition of what those two things are. And they're actually really simple, and we're going to start with momentum. Now, momentum is defined by the variable p, and that is momentum. And the equation for momentum is p equals mass times velocity, which can be shortened to P equals mv. And there's no specific unit for momentum, so we're just going to say momentum is defined in kilograms. See, that's mass, kilograms times velocity, which is meters per second. Alright, and impulse is the product of the net force acting on an object and the time interval, which is delta t. So it is the sum of the forces times the change in time. And with these two things, we can construct our equation for Newton's second law, which is right here. Newton's second law. The rate of change of linear momentum of an object is directly proportional to the net external force impressed upon it. And the common equation for this is the sum of forces equals the change in momentum over the change in time. And since we can assume that mass is going to remain constant through this action, through the problem, and we'll get back to if it changes later, assuming mass is constant, the change in momentum is going to be mass times the change of velocity, because if P equals mv and this isn't going anywhere, then the only thing that can change P is going to be B. And so, assuming that happens, we can change our equation to this, and you might recognize that part, that equals acceleration A. And so we can say that the sum of forces equals mass times acceleration, according to Newton's second law. And this is the most common one that you'll be using. This is important right here. This one. You'll be using this mostly, especially in the two problems that we're just about to hit. And so, without further ado, let's go on to those two problems. And so, here's our first one. When a golf club strikes a 0.046 kilogram ball, the latter may attain a speed of 70 meters per second during the collision. And so we're going to find the average force exerted by the club on the ball. And I forgot to put this in, but the collision is half a millisecond, which is this number. And so what I usually like to do when I'm doing these problems is let's define all of our variables. So we have the ball, and remember what we're trying to find here is the sum of the forces. So what is that? Keep that in mind. And let's go through our variables, and our variables are, so in IB land, we use u, this is initial velocity. The initial velocity of this ball is going to be 0 meters per second, because, the ball's not going anywhere at the beginning of this, and the ending velocity, v in IB land, is going to be 70 meters per second right there, and the time is going to be 0.0005 seconds right there. And so in our equation delta F equals ma, and that's what we need to get the answer. Remember, this is our question mark right there. And we know the mass, that's one other thing. The mass is 0.046 kilograms. So we know that mass, we can get that mass in there. But what's our acceleration? What is that? Well, we know the parts to the acceleration equation, and acceleration equals delta v over delta t. And since t is always 0 at the beginning, we can just say that delta t equals this number. And so we can put in our equation, put this away for just a second, we can put in our equation, since the change between 0 and 70 is 70, we can put 70 meters per second over 0.0005 seconds. And let's pull up our calculator. Our calculator will say that 70 divided by 0.0005. Since that's less than 1, we're going to get a big number. That is a big number. It is 140,000 meters per second squared. And remember, this is just a very small amount of time, so it makes sense that there's such a high acceleration when the club hits the ball. And so with our acceleration, we can now put this in there, boom. And so the sum of our forces is going to equal the mass, which is 0.046 kilograms, times our acceleration, which is 140,000 meters per second squared. Alright, and so in green, let's put our answer. In green, our answer is, according to our calculator here, 0.046 times 140,000. It's going to be 6,440 newtons. And we're going to go to 2 sig figs here, so that's going to equal 64 kilonewtons. Those are equal, and that is our answer right there. So that gets that one out of the way. And for the second one, we have a kind of special presentation. The second problem that we have here is during a particular rocket-powered sled run, Colonel J.P. Stapp of the United States Air Force decelerated from a speed of 286.5 meters per second to a dead stop in 1.4 seconds. Assuming he weighed 175 pounds, which, provided by the textbook, is a mass of 79.38 kilograms, compute the average force. And so, to do this, we actually have a picture here of Mr. Stapp in his fateful journey. And we'll be quick here. We're going to add in the one thing that they couldn't get in this picture, obviously, was the wall. Let's just add that in there. That is the wall Mr. Stapp's going to hit, and the answer that we're looking for, it's going to be in green. Remember, the thing that we're looking for is this force. What is this force? What is that force? So, keep this in mind as we go through, and put this over here, cover up Mr. Stapp for a few seconds, and let's define our variables. And so our variables are going to be, we know the initial velocity equals 286.5 meters per second, and our ending velocity is a grisly 0 meters per second, and the time is 1.4 seconds. So we got these down. Oh, and mass. I keep on forgetting mass. Mass of Mr. Stapp is going to be 79.38 kilos. And so we have our equation for the answer. The answer is this. Delta, or not delta, sum of forces equals MA. And we can put in M right there, but we don't have our A. And our answer is going to be this. Or rather, let's do that in green. Our answer is going to be this. Keep a little consistency. And so, in order to find A, what do? We define what delta V over delta T is, because remember, that is what A equals. And so we can put our variables in here. And so delta V between 286 and 0, well, in order for 286 to become 0, we got to have the delta V be negative 286.5 meters per second. And then that is over our time, which is 1.40 seconds, which is a very scary number for deceleration. And let's put this in our calculator here. And that will be 286.5, make that negative, and divide that by 1.4, and we're gonna that's gonna equal our acceleration, which is equal to negative 204.6. That's meters per second squared. And all right, so in our final equation, the sum of forces equals mass times acceleration, and we know our mass is 79.38 kilos, and then our acceleration right there is negative 204.6 meters per second squared, Alright, and so what is our answer going to be? Put this in our calculator here. It's going to be 79.3 times 204.6 and make that negative. Bam! We have sum of our forces equals negative 16,224.78 newtons. And since we have two, well, that's should be 0, 3 sig figs here, we can change this to negative 16.2 kilonewtons of force. And despite however scary a number that is, Mr. Stapp did survive.